So this is where we were. Okay, we prove that pi is transcendental, right? By using Lindemann's theorem. Okay, let's now go ahead. Okay, so let F be any field. Okay, now corresponding to this, I make this new construction F round bracket X. Okay, slightly different from polynomial ring. When we say polynomial ring, we take F square bracket X like this. Here we take round bracket. Round bracket means you are not considering all polynomials, you are considering all rational functions, polynomial divided by polynomial. Okay, so F round bracket X is equal to all ratios fx by gx where fx gx are polynomials over f and gx is non-zero. Okay, so set of all rational functions over f. So check that f round bracket x is a field. Okay, check yourself. Very easy. This is actually a field because you have these ratios where the denominator is non-zero. So this will be a field. You will be able to import elements. Okay. In particular, the variable itself x, the monomial, right? This is an element of f of x or f round bracket x. This is x by 1. Okay. So this is an element of this field f round bracket x. F round bracket x is a field extension field over f itself. Okay. So we are concerned with the extension field f round bracket x over f. And x is an element in this extension. Okay. So now suppose x is algebraic. Okay, we'll show that as an element of this field, this is in fact transcendental. Okay, so suppose x is algebraic over here. Then there is some monic polynomial f little y in capital F y. So I'm writing y because x is already taken here. Right. So there is some monic polynomial f little y over f such that f evaluated at this point x is 0. Right, by definition. But now here's the thing, x is an indeterminate, right? X is like a variable. So if f of x is 0 or f of y is 0, it is the same thing. So, but f evaluated at x is a polynomial in capital F square bracket x. It's a polynomial. So if f of x is 0, then it means f of y is 0. It's just renaming the variable. But f of y is 0 is not possible because f of y is monic. We said f of y is monic, right? So that is the contradiction. for a very, very simple, or rather, very, very obvious reason, we get a contradiction. Therefore, X cannot be algebraic, X is transcendental over. Okay, so this extension F round bracket X over F is a transcendental extension. Is that okay?
Yes, sir.
Okay, so that was a little bit about examples and what. Now let's move to some very simple properties. So first of all, let's look at a property about transcendental elements. So we just saw that the variable is actually a transcendental element, right? The variable in the field of rational functions over the base field f. The variable x, which is an element of the space of rational functions over the base field f in that variable itself, the variable is transcendental, right? So what are other properties of transcendental elements? So in fact, it says most transcendental elements look nearly the same. There is no distinction between. Okay, so let K over F be a field extension, right? And if alpha beta are two elements in the extension, which are both transcendental, then in fact F square bracket alpha, F round F square bracket beta, F square bracket the indeterminate, right? Polynomials in X over F, polynomials evaluated at alpha over F, polynomials evaluated at beta over F, they are all essentially the same thing. All these vector spaces are isomorphic to each other. In other words, what this says is a transcendental element is just like a variable. The space of the polynomial space does not become any smaller after evaluation. It is just like an indeterminate. Okay, so how do we prove this? So let's just consider alpha and take this function phi alpha. Take this back phi alpha. What is this to goes from fx to f alpha? It simply takes a polynomial fx and evaluates it at alpha. Fx gets mapped to f at alpha for all polynomials. Right. So this is a ring homomorphism. Right. That is easy to check. Okay. What is the kernel? In order to show that this is isomorphic, you only need to show that the kernel is zero. You see, because this is already surjective. Right? For anything that is in f alpha, take that expression in alpha, consider the corresponding polynomial in x. Its evaluation will be this expression in alpha. So this map is actually surjective, that is easy to see. So in order to show isomorphism, you only need to show that this is injective. Injective means kernel is zero. That's all you need to show. Right? So consider kernel of phi alpha and suppose it is non-zero. Okay, we go by contradiction. Suppose the kernel is zero, which means there is a non-zero polynomial little fx, which is an element of the kernel. But now let me write down what fx looks like. So fx, let us say, it looks like some b0 plus b1x plus b2x squared up to some big x raised to n for some b0 to bn. And we are assuming that the leading term is 0. So let us say bn is non-zero. If Pn is non-zero, we can easily form a monic polynomial out of this, right? So we can take g alpha of x to be 1 by Bn times f alpha of x, right? Bn is non-zero in the field K, so I can invert. So 1 by bn times f alpha x. Right? Oh, not k. This is f. So that's the typing mistake. This is f. Okay. So now when I take 1 by bn times f alpha, this is actually monic polynomial. Right? G alpha x is monic polynomial. But further, f alpha x is actually in kernel. So f alpha at alpha is 0. And therefore G alpha at alpha is also 0 because it is 1 by bn times f alpha at alpha. So G alpha x is a monic polynomial which vanishes at the point alpha. And it's a polynomial over the field f, which means alpha is algebraic over f. Right? But alpha is given to be a transcendental element. Alpha is a transcendental element. Right? So that's a contradiction, and therefore the kernel is actually 0, which means phi alpha is injective, therefore it is an isomorphism. Okay. So as I just said, also it is easy to see that phi alpha is surjective. So by first isomorphism theorem, the image which is f square bracket alpha is isomorphic to the polynomial ring f square bracket x divided quotient with kernel. Kernel is 0, so polynomial ring quotient is 0, which is the polynomial ring itself. So the space of polynomial expressions in alpha is isomorphic to the space of polynomial expressions in polynomials. Similarly, we can show that f beta is isomorphic to f x, and therefore we get both f alpha isomorphic to f beta. Is this much clear, everybody?
Yes, sir.
Okay, good. Okay. So another small result about field extensions. So suppose k over f is a field extension, and alpha in k, the extension field, is algebraic over f, the base field. Then there is a unique monic irreducible polynomial fx in over the base field f, such that f at alpha is 0. So by definition, there is some monic polynomial such that f of alpha is 0. But if you also put the condition irreducible, if the polynomial is also supposed to be irreducible in the polynomial ring fx, then it is a unique choice. There is only one such irreducible polynomial. Okay, there is only one such irreducible polynomial. That is the message from this design. Okay. So how do you prove that? So now let me go to the notes. Okay, so now this proof is already given nicely in the notes, in those other notes. So it's the file new proofs1.pdf. So I'll just take you through the proof there. There is a slight typing problem. So f and k have been interchanged. Okay. They work with k with the extension f over k instead of k over f, but that is not a big deal. You write down in terms of k over f and practice later after this class. All right. So this is proposition 2.4. So let's go there. Okay. So they are dealing with f over. So now base field for them is k and extension field is f. So let f over k be field extension and alpha be an algebraic name for k. Then there is a unique irreducible polynomial that f over k such that f alpha is c. What do we know? We know that there is always a monic point by definition which satisfies this property. We want to say that if it is irreducible, then it is weak. Right? So what do we do? Well, just consider the polynomial ring kx over the base field, okay, and consider the evaluation. It's basically the same map that we just saw earlier. Okay? Evaluation at alpha. We called it phi alpha, they call it psi. That's why. Take a polynomial gx and the answer is gx evaluated at alpha. Okay. So now we analyze this slightly differently. This is a ring homomorphism. Alpha is an algebraic element, right? So there is a non-zero polynomial such that this will vanish. There is a non-zero polynomial gx such that g of alpha is 0. Therefore, the kernel of this map is a non-zero ideal. It's not the zero ideal anymore because alpha is algebraic. Earlier, alpha was transcendental in the previous result, so we showed that kernel is 0. But now alpha is algebraic, therefore this kernel is non-zero. Okay? So non-zero kernel. Do you remember that the kernel of a ring homomorphism is actually a prime ideal? Always. Okay, it's always a prime ideal. But kx is a PID, right? Kx is a PID, therefore you have every prime ideal is maximal. Okay, kx is a PID, every prime ideal is maximal. So I is in fact maximal ideal. When it's a maximal ideal, kx mod I is a field. Remember, take a ring homomorphism, then the domain ring mod a prime ideal is an integral domain, domain ring mod a maximal ideal is a field. This is a characterization. Right? This is a statement from ring theory. Have you done this? Are you familiar with this?
Yes, sir.
Okay, okay. So kx is a PID, therefore every prime ideal is maximal. So kx mod I is in fact a field because I is maximal. Right? So kx mod I is isomorphic now. By isomorphism theorem, it's isomorphic to a subring of F, right? It's isomorphic to its image inside F. But it's a field, therefore it's isomorphic to a subfield of F. Okay. Further, I is maximal, so it is generated by an irreducible polynomial. I is maximal in a PID, so it's generated by an irreducible polynomial. Just like a prime ideal is generated by a prime element, maximal ideal is generated by an irreducible polynomial. Let's call that Hx. Okay. Now there are two polynomials that we are considering. Okay. We are fixing a g of x that we get, which shows that alpha is algebraic. It's a monic polynomial over k such that g of alpha is equal to 0, due to which we said that the kernel is non-zero. Okay, that is a polynomial g. And now there is another polynomial h, which is known to be irreducible, which is the generator of the kernel. Okay, so g of alpha is equal to 0. We know that. Therefore, it is in this ideal, but this ideal is generated by hx. So gx is in fact hx times some other polynomial h1x, right? Because hx must divide this, because gx is in the ideal generated by hx. Okay. What else do we know? So what we have said is that if g is a monic polynomial set which vanishes at alpha, then g is in fact a multiple of the irreducible generator of the kernel. Okay. Further, if we say that g is should be irreducible, not just monic polynomial vanishing at alpha, if we say that we want a monic polynomial which is irreducible and vanishing at alpha, then an irreducible polynomial as a multiple of another irreducible polynomial can only be by scalar multiplication. Okay, so g is in fact some. It is not supposed to be alpha. Okay? This is some other scalar theta. That's a printing mistake. So g is in fact some scalar times hx then, because both are irreducible, right? But if we say both have to be monic, then they have to be equal now, because monic means the scalar becomes 1. Okay, so if you want a monic irreducible polynomial that vanishes at the given algebraic element alpha, then it must be equal to the irreducible generator of the kernel. It cannot be anything else because it is in the kernel since it vanishes. And since it is irreducible, it is a scalar multiple of the irreducible generator. But then since it is monic, the scalar has to be 1, therefore it has to be equal to the irreducible generator. Do you understand or do you want me to repeat this? Hello, do you understand? What is it?
Yes, sir.
Yes means what? Do you want me to repeat it? What is going on? If you भी अगर आपको लगता है कि बाद में जाके रिकॉर्डिंग देख के सीख लेंगे, it is going to be difficult. Okay? डाउट है तो पूछो, अभी पूछो. Okay, so in summary, what we are saying is, for any algebraic element, if you take the corresponding evaluation map, just the homomorphism defined on the polynomial ring, where every polynomial is evaluated at that algebraic element. Okay, it's a ring homomorphism. But since it's an algebraic element, there is at least one non-zero polynomial which evaluates to 0 at the point. Therefore, the kernel is a non-zero ideal. But kernel is a non-zero ideal. This polynomial ring is a PID and everything. So the kernel is actually a maximal ideal and generated by a single irreducible polynomial. And the quotient is in fact isomorphic now to a subfield because ideal is maximum. So here's the thing. Now, if you want the vanishing polynomial g of x to be irreducible, then you will say that since it is the kernel, it is a multiple of the irreducible polynomial. But irreducible as a multiple of another irreducible means they are multiples only by scalar multiplication. So the vanishing polynomial g is in fact just a scalar multiplication of the irreducible generator h of the kernel. But then if you also say that the polynomial must be monic, then the scaling multiple must be 1. And therefore, the vanishing irreducible monic polynomial is in fact equal to the irreducible generator of the kernel. Okay. So whatever be the polynomial, if it has to be irreducible and unique, it must be equal to h, and h is unique. Right? Therefore, there is a unique monic irreducible polynomial such that f alpha is 0 and alpha is zero. Okay. So that is the proof. Okay. So there is a unique monic irreducible polynomial. So we can actually make an identification. We can give it a name. We can give it a notation. Okay. So now we are back to our notation k over f. Okay. So let k over f be a field extension and alpha in k, which is the extension field, upper field, be algebraic over the base field. The unique monic irreducible polynomial, obtained by this proposition, right, 1.3, will be called the minimal polynomial of alpha over the base field f. Okay, in some sense, it's the smallest polynomial that vanishes at alpha, smallest non-zero monic polynomial, right? Minimal polynomial of alpha over f, and we will denote it this way. It is irreducible, right? So we'll denote it by IRR alpha comma f of x. X is the indeterminate. So the irreducible, minimal irreducible polynomial of alpha over the base field f and variables is x. Okay. And we say the degree of the element alpha over f is just the degree of this minimal polynomial. The degree of the element alpha is defined to be the degree of its minimal polynomial. Okay. Now let me quickly mention a comment. Okay. So algebraic elements are the ones which will have some such minimal polynomial vanishing at that point, right? Algebraic elements will have a polynomial, will have a monic polynomial vanishing at that point, and therefore, as we just saw, there will be a minimal polynomial. So there is a polynomial. Okay. Round off, the message is that there is a polynomial with finite degree which vanishes at that point. Okay, so think of this degree as some indicator of how difficult it is to compute that element alpha. Okay, think of the degree as a measure of difficulty of computing that element alpha. So degree 1 element is easier than a degree 2 element. A degree 5 element is much harder than a degree 3, degree 4 element, and so on. Okay, so elements with finite degree, right? Elements which will have a polynomial with a finite degree vanishing at that point, these are algebraic elements. Elements which don't have that, elements for which there is no polynomial with finite degree which vanishes on them. These are the ones that are not algebraic. They are called transcendental elements. So in effect, you can think of transcendental elements as having infinite degree. Okay, they are much more difficult to compute than algebraic elements. Okay, if degree indicates difficulty, algebraic elements have finite degree, finite difficulty to compute them. Transcendental elements are the ones which have infinite degree. Okay, much more difficult to compute them because they don't even have a polynomial which vanishes at them. Okay, what I just said is very informal, but it is a good way to understand the difference between algebraic and transcendental elements. Is that okay, everybody? Okay. So let's now look at some examples of, well, it's more or less the examples that we just saw. Let us also compute the minimal polynomial and the degree. Okay, over examples that we've just seen. So for any field f, any alpha in f itself is trivially an algebraic element. It is a root of the polynomial x minus alpha. Now, do you see a monic polynomial a non-zero polynomial must have degree at least 1. So this is a linear polynomial of degree 1 itself. So this must be the minimal polynomial. Okay, linear factors are irreducible also. Okay, so this is monic with degree 1, so it's trivially irreducible. So, and any monic polynomial that is non-zero must have degree at least 1. Therefore, x minus alpha is the irreducible minimal polynomial of alpha over f. Okay, so IRR alpha f is actually x minus alpha, and the degree is 1. And this is not a surprising statement. For any element in the base field itself, its degree over the base field is 1. That's what this is saying. Right, next example that we have seen, taken in natural number 10. Then square root n is a root of the monic polynomial x squared minus n over q. Right? The square root n is algebraic over q. Now, does that mean that the degree of square root n is 2? Does that mean that this polynomial is irreducible? Not necessarily, right? There are two cases. Okay? So if n is a perfect square, sorry, if n is not a perfect square, okay, which means square root of n is not an integer. Okay, it's not a perfect square. Square root n is not an integer. Square root n is irrational. Okay, so if n is not a perfect square, then you can check that square root n is not a rational number. It is irrational. The proof is similar to the proof that square root 2 is irrational. Okay, so check that yourself. Check that yourself. square root n is in fact irrational when n is not a perfect square. Okay, it is irrational. So this polynomial x square minus n actually splits as x minus square root n, x plus square root n, right? Yeah. Okay. So if f of x in the rationals is a monic polynomial that vanishes at square root n, if it has degree 1, suppose possible it has degree 1. The degree 1 irreducible polynomials are just of the form x minus alpha for some alpha. Therefore, fx must be x minus square root n because it is degree 1 monic and vanishes at square root n. So it has to be x minus square root n. But square root n is not rational. It's an irrational number. Therefore, fx is not here. So the degree of the minimal polynomial cannot be 1. This fx is not a minimal polynomial. Okay. For the same reason, since square root n is not rational, the other factor x plus square root n is also not a polynomial, not a polynomial over Q. Therefore, this monic polynomial x square minus square root n, which can be factorized uniquely as x minus square root n plus x minus square root n times x plus square root n, both of these factors are not over Q. This factorization does not hold true over Q, right? So over Q, this does not factor. It factors over the complex numbers or over the reals, but over Q, over rationals, it does not factor because square root n is irrational. Therefore, this is irreducible over Q because it does not factor over Q. So it is irreducible over Q, right? So degree, so this is indeed the monic reducible polynomial or the minimal polynomial of square root n over Q. So IRR square root n over Q is just x square minus n and the degree is 2. Okay, so when n is not a perfect square, square root n is irrational and its degree over Q is 2. However, if n is a perfect square, that is n is of the form k square, k is some natural number, right? Then square root n is k, it's a natural number. So it's a root of the monic polynomial x minus k. See, k is an integer, so k is a rational number. So this linear polynomial x minus k is a polynomial over the rationals. This is in other words x minus square root n. And this vanishes at the point square root n, right? So it's degree 1 monic polynomial which vanishes at the point. So it is the irreducible polynomial. It is the minimal polynomial. So minimal polynomial square root n over q in this case is just x minus square root n because square root n now is an integer. And the degree is 1. Okay. So square root n for any natural number n is algebraic over q, but the degree depends on whether it is a square or not. If it is not a perfect square, then the degree is 2. If it is a perfect square, then the degree is only 1. Is this much okay? Okay. Rishabh? Rishabh Mishra.
Yes,
समझ में आ रहा है मैंने क्या कहा?
yes,
पक्का?
हाँ sir.
नीलम? नीलम खड़गे. नीलम खड़गे.
सर उसका थोड़ा नेट का इशू चल रहा है, उसने बोला था।
अपर्णा? अपर्णा लाटे?
Yes, sir.
So are you able to follow? Is there any doubt?
यस सर सर आज ना नेटवर्क इश्यू है तो मेरे को स्क्रीन ही नहीं दिख रही.
तो आप क्या करने वाले हो? क्या आइडिया है आपका? कैसे कवर करोगे?
सर फिर से देखूंगी ना रिकॉर्डिंग.
ठीक है, ओके. Okay, let's go to another example. So now we just saw that any rational complex number, right? Any complex number of the form a plus ib, where a and b, both real and imaginary parts, are rationals. This is algebraic over Q. Algebraic over the rationals. So what is the irreducible polynomial? What is the harmonic polynomial and what is the degree? Okay. Again, there are cases. Cases depending on whether it is a real number or not. Understand? Whether it's a real number or not, that brings. Am I audible? Ah, okay. So whether it's a real number or not brings two cases. So suppose b is equal to 0, which means the imaginary part is 0, which means the number is just real. Okay. But over the rationals, so z is in fact just the rational number a, nothing else. Therefore, you can just take the polynomial x minus a. It's a harmonic polynomial over the rationals, which vanishes at the point. So this must be the minimal polynomial over of z over q, and therefore the degree is 1. But now if that number is not purely real, okay, it is a complex number non-trivially, so the imaginary part is non-zero, then z is equal to a plus ib, as we have seen before, okay, in the previous discussion. It is a root of the monic polynomial x square minus 2a times x plus a square plus b square. Right? This we have just seen how it comes. And this is a polynomial over the rationals because a and b are rationals. Okay. Now, is this the minimal polynomial? Is the degree 2? So let's check. If it is not, can the degree be 1? So monic polynomial of degree 1 that vanishes at a point must be a linear factor of the form x minus alpha. There is no other choice, right? So monic polynomial of degree 1 that has z, this given complex number as its root, must be x minus z. There is no other choice. You cannot come up with another monic polynomial of degree 1 that vanishes at that point. It has to be this. But now imaginary part is non-zero. So this is not a polynomial over qx. This is not a polynomial in q. It's not a polynomial over qx because the imaginary part is there. I is there here in the coefficient. So this is not a polynomial over q, right? So the degree of the minimal polynomial must be at least 2. And there is a polynomial of degree 2, right? So this is the minimal polynomial, x square minus 2ax plus a square plus b square. This is the minimal polynomial of z over q, and its degree now is 2. Okay. So in this case, the cases are depending on whether the number is purely real or not. In this case, purely rational or not. Okay. Another example. This example is very interesting. Okay. It's quite related to what we were seeing earlier also. The computation is a little more involved. So let us take square root of I. It's a complex number. Okay. Whatever that element be, it's a certain value. But the square of that number is I. Okay. And that is how it is defined. So we take square root of I, which is a complex number. Okay. So what is square root of I whole raised to 4? It is I square, which is minus 1. Okay, so whole raised to 4 is minus 1. Therefore, it is a root of the monic polynomial x raised to 4 plus 1. See, when you raise it to 4, it is minus 1 plus 1 is 0. So square root I is a root of the monic polynomial x raised to 4 plus 1. This is a polynomial over the rationals clearly. Okay. Now let us say that this is the lowest degree polynomial you can find. You cannot go any further below as long as you are working over Q. Okay. So by contradiction, suppose x raised to 4 plus 1 is reducible over Q. Right? What does that mean? It factorizes properly. X raised to 4 plus 1 factorizes properly as a product of two polynomials, Px and Qx over Q. So Px and Qx are polynomials over Q, proper factors. Therefore, their degree must be at least 1. Degree of P and degree of Q both must be at least 1. Further, x raised to 4 plus 1 is monic. So we can assume that P and Q are both monic. That is not a big problem. But now degree of P and Q are both at least 1, but the sum of their degrees is 4. So there are only two possible cases, right? One is the degree of one polynomial is 1, the other polynomial is 3, because the degree should add up to 4. The other is that both polynomials have degree 2, so that they again add up to 4. So let's consider the first case. Suppose degree P is equal to 1, degree Q equal to 3 without loss of generality. Okay, if Q has degree 1, P has degree 3, then we will switch them and argue similarly. So without loss of generality, suppose degree P is 1 and degree Q is 3. So P must be of the form x minus a for some rational number a, because it's a polynomial over the rationals with degree 1. So x raised to 4 plus 1 evaluated at square root of I is 0. So square root I is a root of either P of x or Q of x, right? If this at square root I is 0, if this at square root I is 0, then either P of square root I is 0 or Q of square root I is 0. But P is just x minus a, which is where a is rational, so it is 0 only at a. So P of square root I cannot be 0. Okay, because square root I is not a rational. Therefore, Q, the other factor with degree 3, right? Q vanishes at square root I. Q at square root I is 0. That's the important part. Okay. Now, this is a basic fact that you all have seen in BSc. You take any polynomial over the reals, not even over the rational, in fact, over the reals. If a complex number is a root of that polynomial, then the complex conjugate is also a root of that polynomial. Remember, roots of polynomials over the reals come in pairs. The complex number is a root, its complex conjugate is also a root. So Q of square root I is 0, therefore Q of square root I bar is also 0. Conjugate of square root I is also 0. We don't know what Q looks like. That is okay. We only know that degree of Q is 3. Okay. Now I, if you write it down, I is what is it? If you write it down as cos theta plus I sin theta, you want cos theta to be 0, sin theta to be 1. So the angle theta is actually pi by 2. Right? So I is equal to e raised to I times pi by 2. Okay, check that. Therefore, square root I is just e raised to I times pi by 4. Right? The power comes down by a factor of 1 by 2. But more importantly, the complex conjugate, when you write it this way, it just introduces a negative sign. So the complex conjugate of square root I is in fact e raised to minus I pi by 4. Right? So now when you write down what these two are, e raised to I pi by 4 is cos pi by 4 plus I sin pi by 4. That is 1 by square root 2 plus I times 1 by square root 2. Similarly, square root I bar is in fact 1 by square root 2 times 1 minus I. 1 by square root 2 minus I times 1 by square root 2. So these are these numbers actually. How did we find this? We found this by looking at the angle. Okay, we looked at the angle of I, therefore the angle of square root I must be half of that, right? And then we evaluated this. Okay, so clearly square root I is not equal to its conjugate. If it is equal to its conjugate, it's a real number, but it's a complex number, so it is not equal to its conjugate, right? So q of x, which is a polynomial over the rationals, already has two roots, square root I and square root I bar, right? But q has degree 3. So if you write it down as a product of linear factors over the complex numbers, this is in fact x minus square root I times x minus square root I bar times some one more root x minus b, where b is some complex number. That's all. But what square root I and square root I bar are. So when you combine them, check this calculation. I have written it directly. X minus square root I times x minus square root I bar is in fact x square minus square root 2x plus 1. Okay, check that. So this is this polynomial times x minus b, which expands to this x cubed minus b plus square root 2 times x squared plus b into square root 2 minus 1 times x minus b. Okay. But if this is true, q of x is a polynomial over the rationals, which means every coefficient is a rational number, which means b is a rational number. But if b is a rational number, b plus square root 2, which is the other coefficient, that is not a rational number. Therefore, q is not over the rationals, which is a contradiction. Understand? So what have we got here? We have not got anything. What we have got here is the following. Okay. We are assuming that x raised to 4 plus 1 is reducible over q. Then we are getting two cases depending on the degree of the factors. For the first case, when one of the polynomials is degree 1 and the other polynomial is degree 3, we are getting a contradiction. That means that this case cannot arise. That means x raised to 4 plus 1 is not a product of two polynomials with one of them having degree 1 and the other one having degree 3. That is what this is. This case, when we analyze this, we get a contradiction. Therefore, this case is not true. It cannot happen. Right? What is the other case? The other case is both factors have degree 2. So again, let us assume without loss of generality that q vanishes, square root I vanishes at the polynomial q. Okay, because it has to be a 0, either p or q, both have the same degree. So again, without loss of generality, suppose it's a root of q. Again, it's a polynomial over reals. So if z is a root, then z bar is a root. Right? So we have already computed this. So square root I and square root I bar are two distinct roots of q. Now q has degree 2, so these are the only roots. So it is a monic polynomial and therefore it is equal to this product. X minus square root I times x minus square root I bar, which we have just seen is in fact x square minus square root 2x plus 1. Qx is equal to this polynomial, but Qx is a polynomial over rationals. Again, we get a contradiction because one of the coefficients is square root 2, which is not a rational. So even this case is not possible, right? So both the possible cases are false if you assume that x raised to 4 is x raised to 4 is reducible over q. If you assume that x raised to 4 splits as a product of two polynomials of smaller degree, you get two possible cases. Both possible cases are false. In both cases, you get a contradiction. Therefore, x raised to 4 does not factor, does not split into product of two factors. In other words, x raised to 4 plus 1 is irreducible because in both cases we get contradiction. So then what we assumed at the beginning is wrong. So x raised to 4 is irreducible over q. And therefore, monic irreducible polynomial is unique. So this has to be the minimal polynomial of square root I over q. And therefore, its degree is 4. Not 1, not 2, it is 4. Okay. So degree of square root I over q is 4. Okay, so that's where we are. A small note now. Let us change this. Okay, so do you remember Q square bracket I was a field? We proved that. But we know that I is algebraic over Q. So Q square bracket I is in fact equal to Q round bracket I. Okay, every polynomial is in fact invertible. It's a rational expression. So I'm just changing the notation and saying this as Q round bracket I. Okay, every rational expression is in fact a polynomial, so it's not a big deal. Okay, so now instead of looking at square root I over the field Q, let us look at square root I over the field Q adjoint I. Okay, so clearly I belongs to Q adjoint I, and square root I is the root of the monic polynomial x square minus I, right? Square of square root I is I minus I is 0. So it's a root of the monic polynomial x square minus I, and this is a polynomial over the base field Q round bracket I. Okay. The extension field is complex numbers, as usual. Okay, but the base field I have changed it to Q adjoint I. The important thing here to note is that square root I does not belong to Q adjoint I. You see, because even if these are rational expressions, even if these are rational functions, the coefficients have to be rational. But square root I we have just seen is actually 1 by square root 2 times 1 plus I. So square root 2 is irrational. So this cannot be here. This cannot be. So square root I is not an element in Q adjoint I. Okay. So check this. I just told you why, but check this again. And then x square minus I can split only as a product of x minus square root I times x plus square root I. Right? But both of these factors are not possible over Qi because square root I is not an element here. So this factorization is not true over Q adjoint I. It's true only over complex numbers. So over Q adjoint I, x square minus I is irreducible. Because if it reduces, it has to be this, but then both of these factors are not polynomials or not functions in Q adjoint. So it is irreducible over Q adjoint I, it is monic. Therefore, it must be the minimal polynomial of square root I over Q adjoint I. So the minimal polynomial of square root I over Q adjoint I is x squared minus I, and its degree is now 2. Okay, over Q the degree was 4, over Q adjoint I the degree is 2. Okay, so is that okay? That is the end of some examples. Then we have some more statements which we do next time. So I'll stop here. Any doubts, anybody? Okay, so let us stop here. Tomorrow we'll meet in the morning for Python and then we'll see. So if there is a free lecture, we will do algebra, but otherwise morning we'll do Python. Okay, so I'll stop.